the ground and into the sky, perhaps only coming back to Earth when it's flown halfway around the world. And I bet for most of us, the total mystery how such a heavy object stays in the sky at all and doesn't just plummet back into the ground.
My name is John Durant, and I carry the rather unusual title of Visiting Professor of the Public Understanding of Science at Imperial College in London. I've done some detailed research into how much people really know about science, with the help of a series of questionnaires and other tests. And I've unearthed a paradox. British people seem to know very little about science, even though, according to our research, they're keener to learn about it than about politics, or films, or even sports. To discover why science is so hard to understand, we've challenged 3 volunteers to try to learn in a week just why planes manage to fly. The problem shouldn't be a lack of information. James, a retired taxi driver, often listens to the radio, which offers several specialist science programs. And Mandy, who works as a barmaid, just as easily finds herself watching science programs on TV. Tara's job as a mum, eager to help Harry learn new things, gives her the chance to visit the Science Museum, so she too has had access to some sort of scientific information. But if more information is all that they need, where better to start than at Cambridge University, with its tremendous reputation for science? I was sure that they could find a textbook explanation here of why things fly, and I pointed them in the direction of the Science Periodicals Library.
In an airflow of constant density, moving at subsonic speed, pressure and velocity are related inversely.
As the air which is sending up flowing over the curve at the surface of an airplane wing will give a reduced pressure.
Since the air flowing below the wing is slow, giving a higher pressure, lift is generated.
Hello, so how did you get on? What did you make of that explanation of why planes fly? Huh? More or less nothing. Mandy? Not really anything too much. How about you, James?
Well, I think it's something to do with pressure.
Something to do with pressure. Yeah, okay, well that's a start, but there's a lot more in that you really couldn't make much sense of. Okay, well not to worry, at least we know the size of the challenge that we're going to take on. Now let's think about it for a minute. Information can't be the thing that's holding you back. After all, we've seen there's bags of that around. But just to make sure that you're really motivated to find out how planes fly, I'll open a bottle of champagne in a few days' time if you can answer a simple question based on what you've just read. But before we do that, perhaps you should just think a bit about what's involved in learning anything.
It seemed important at this point to show Cara, Mandy and James that real understanding of how something works may depend much more on experience than simply reading a textbook. So much to their surprise, I introduced them to a lawnmower. That's because psychologists are discovering that practical experience is an essential first step to understanding something. A 4-year-old, when asked to balance something like this, will typically feel the point of balance. It doesn't matter what shape or size the object is. Each time a new object has to be balanced, the same feeling for where it balances takes place. Now watch what happens with older children. At first sight, they seem to have forgotten how to feel for the point of balance. With an unevenly weighted object, they quickly decide that it cannot be balanced. In fact, these children have made progress from the repeated practical experience of feeling the balance. They've developed a simple theory that things balance in the middle. It often proves correct, so they cling to the theory, simply rejecting objects that won't balance in the middle as unbalanceable. At the next stage of development, further practical experience has helped the child reject the simplistic early theory that things balance in the middle as being inadequate. And now there's a new, more sophisticated theory to explain balance.
What did you do to put the fun in? So what just happened? Why does my name come so?
So back to the lawnmower, to see if by the time we're adults we can manage to learn from theory alone. Here's the theory. It's the manual for the mower. I'll give that to you, James. And I'm going to take this mower away and disable it, and then give you a chance to try and work out what's gone wrong with it using only theory and no practice.
See, this page is all about roller and cutter assembly. Well, it's broken down and it'll be possibly engine, won't it?
Yeah.
So I think we've got to find, we've got to find a page about the engine. Preparing well for use, safety rules. Right, so it could be something.
It's difficult to do this
It's
until the
the
mower.
Yeah. It's the
The
best.
mower might start.
Yeah, well, yes.
Chris might not cut the grass.
Well, hello. This is not an entirely happy lawnmower. The blades are not going round, as I think you may have seen when I walked across, and I can tell you also that the roller isn't going. I had to push this, it wouldn't pull. So, how do you think you can get on just with the manual to start with, telling us what you think's wrong with this?
Right. So I've got to turn to pages cutting and roller. So we got
Where's
it.
that fault finders page? It might be right next to fault
Right.
Yeah.
Right.
finders. We'll make sure. Other jam. Stop the engine. Remove the mark and turn the blades back. The blades shot. Finish with the glass. Don't know if it's the front roller or the rear roller.
That's true,
We
yeah.
don't get something to do with the cutting assembly.
We haven't done anything to do with that roughly at all. It might be anything to do with that. It might be just
So you
the
just
rollers.
stab in the dark.
Yeah.
Oh, that's right. That's right.
So, I get the impression you're beginning to think that there's a limit to what you can learn just from the theory, is that right?
Sure, yeah.
Good stuff. Well, how about using a few tools? I've got a few here, and you might find those helpful, and getting a bit of practical experience with this machine.
Now then, you keep somebody look at the manual and tell us what to do with this.
What one shall I take here? Well, should we tackle each of them?
Yes, the blades might be the easiest thing, because at least we can see those.
Right, which one's got
So
to be
that's
in
not
here?
So we need to do that.
Yeah, away you go, mate.
Right. I'm a trivet screwdriver man, I'll tell you that.
I'll read this. To adjust the chain, first we remove the cutting guide, cover line, screw. Loosen nut, L.
Right.
Oh, hang on, this is just construction.
They've messed about with the chain assembly.
It's supposed to look like this.
Yeah, so okay, so that goes on the bottom.
What are these for?
Okay, where there's nothing to wash it. No, I tell you what, no, I know this about, it's the same on bikes, if you put it on the small top first, you'll get it on. Well, hopefully you will anyway. Right. No?
No, we're going to have to just...
No?
This
Take
here
this off,
has
yeah.
to be moved
Oh,
as
you've
well.
got to take that, I see, take it up.
Move adjust the tape inwards or outwards according to the need.
Right.
So,
Hold on, let's back it. No? Okay.
diagram on, James, and see if that looks like it looks.
Yeah, that's right. Well, as I say, if we reassemble it and start the mower,
find out.
we'll soon find out we've left it on it.
Because there we've got the chain
Let's
on.
move it, yeah. Or shall I hold... Oh, wait, don't hold the blades. Pass me the... Hold on a minute.
Okay.
Always right again.
Just let's put the cover on it because we don't want to be dangerous having it. Hold on. Right. There we go.
Well, how about that? You seem to have cured the problem. How much easier was it when you could actually get your hands on the machine?
Well, having seen the diagram, it was recognisable.
Right, so without the diagram it would have been more difficult, but would you have ever solved the problem, do you think, if you hadn't been able to get inside the machine and have the experience?
No, it's pure guesswork.
Hands-on experience of a lawnmower is one thing, but giving Cara, Mandy and James hands-on experience of an aeroplane was much more of a challenge. Which is why we ended up with something rather more elementary, in a hangar sheltering thousands of sparrows.
Well, to understand things, we need some practical experience. So to understand how things fly, we're going to get some practical experience of vehicles and what makes them move, and ultimately, I hope, what keeps them in the air. Okay? What do you feel as you hold them?
Heavy.
They feel heavy. Okay.
Yeah.
Why do they feel heavy?
Because of the weight.
That's right. Things have weight because of gravity, yes? And that is a force that acts on the vehicle whenever it moves. All right? All right, so that's the first of our forces. Now we can move on and equally easily demonstrate the second. If Mandy and James, you'll just push those two vehicles back to Cara and me. Okay, now what was happening there when you pushed them?
Well, just pushed it towards us.
Okay, there's another force involved here. It's actually called thrust. And you were doing, in a sense, I suppose, what the engine in a car or a plane would normally do, pushing the vehicle forward. Right, now there's a third force. We've got two so far, weight and thrust. There's a third one that we can illustrate pretty easily, but we're going to need some parachutes to do that. So why don't you try attaching parachutes to the car and the plane? Now, did you notice anything different that time?
Well, it didn't go so far.
It didn't go so far. And do you want to have a go pushing them back to me? Do they feel any different?
I think you're holding back into that.
Yes. In fact, some airplanes do in fact use parachutes, don't they, to help brake when they land. So what I'm really suggesting is that drag, which is the name for this third force, is a force pulling vehicles back when they try and move through the air. It's a force, if you like, opposite to thrust. There's a fourth force that we want to think about as well. We can't really demonstrate that inside this hangar. We can do it just outside on the airfield.
If two vehicles travel alongside each other at the same speed and acceleration, in other words, the same relative drag and thrust, you can see that at some point in one case, the fourth force, lift, overcomes the first force, weight, and the plane takes off. But of course the car never does, because it never has enough lift to overcome its weight. To find out more about lift, we came to National Power's Technology and Environmental Centre at Leatherhead.
Okay, so we've seen these four forces that we looked at yesterday, that thrust is opposing drag and lift is opposing weight.
Yeah.
The key question, I suppose, Cara, is why the plane took off with lift and the car didn't. Why do you think that was?
Because we have wind, I suppose.
Yeah, that's right. And what we've come to this lecture to do is to look at how we generate lift more exactly. That was pretty amazing. Was it fun? You controlled it quite well. Now tell me, what was going on in there? I mean, what do you think you saw?
I don't know what we saw. We felt more than we
Oh,
saw.
we saw a takeoff.
You saw a takeoff?
Yes.
Yeah. Okay.
Yes.
And what's the crucial thing about the takeoff? I mean, what was causing the plane to take off?
Well, the wind.
Like the wind.
Yes.
Okay, so what we want to think about then is how wind passing across the plane, and particularly across the wings, might cause lift, the key force that gets that plane up off the deck. Now to do that, we're going to do a few simple experiments, at least you are. Now, I want Cara, please, to do something like this. I want you to hold up two pieces of paper, about 6 inches apart, in front of you, and then I want you to blow fairly hard between them. Okay, as simple as that. Before you do it, I want to ask James and Mandy what you think is going to happen when Cara blows between those two bits of paper.
Well, I think the ends of the paper will go out.
They'll go out. Mandy?
Yeah.
You think the same? Okay. Have a go. What happened? Certainly did. Have another go. Did it? It did.
With a gun. Yeah.
Now, why on earth would the paper move inwards when you do that?
Is it sucked in, drawn somehow, with the current of blowing?
It is. I mean, that's what must be happening. Is it then the case that the movement of the air in the middle is causing a lower pressure between the two bits of paper so that the air on the outside is pushing them in?
Oh, I see. The air outside is greater than this.
Pressure on the outside is greater than on the inside.
Why is that? What, you blow, you can move pressure then, as you blow.
Well, it's, I suppose, not so much that you're moving pressure, but simply
moving the airflow is decreasing the pressure of the air. Air that's moving has a lower pressure than air that's still. You can see it another way. I can do the same sort of thing with this single piece of paper, and I'm just going to blow across the top of it. And if we're right, blowing across the top should decrease the pressure on the top side of the paper, so what should happen?
Lift up.
It'll lift up. Let's have a go. There you go. So we've got ourselves here quite an important principle, and it's the principle that when air is in motion, it's got a lower pressure than when it's still. In fact, the faster it moves, the lower the pressure. Okay? Now, let's start thinking about what might be going on then in a plane's wing. And if we move just over here, we've got something that's meant to look a bit like a plane's wing. James, I wonder if you could come and work this machine for us. And Clara, you might like to go to the other side over there and stand by in readiness. Okay, so switch on, place a board bottom.
Is that right?
That's it. Let it work. Okay. And again. And again.
Let's finish on it. I can really relate what we've done there to Clara blowing on the top of the paper. I can really relate to that.
Okay.
I'm struggling a little bit. Am I right in thinking this in theory is just bent paper? So the air coming across?
No, it works a bit like this, I think, that the air being blown across the top is like my blowing across the top of the piece of paper. Now, when I blew across the paper lifted up.
Yeah.
This is fixed, but nevertheless, the air going across the top is creating a lower pressure here. And that lower pressure is, if you like, sucking or drawing balls up through that open tube from beneath, because there's a lower pressure here than there is down here.
Mm-hmm.
So there is actually lift operating on this as a result of that.
Yeah, okay.
Okay?
Oh, well, he's done that.
It's a bit of a cheat in a way, because you've got a plastic tube which you'd never have on a wing.
What was putting you off?
Right, okay.
So there's great pressure from that end. And push the ball up and then into this moving over here.
Absolutely.
Are you saying to us that it's because of wing design that we create an even greater pressure?
Well, that I think is probably true, but the more basic thing I want to get at the moment is how is that plane in the wind tunnel sitting there with wind flowing smoothly all around it? How is that plane managing to take off, to lift? What must be happening from what we've seen here?
Well, the wind must be travelling faster above the wing than it is below the wing.
Exactly right. Now, if the wind were travelling faster across the top of the wing, what would happen? If in that tunnel the wind is going faster across the top surface than the bottom surface,
It could
Lift up.
you've got it. Finally, we return to Cambridge to learn how the design and shape of an aeroplane wing exploits the airflow around it to create lift. We were taken to see a small wind tunnel which can be filled with smoke. When air is blown through from bottom to top, the smoke settles into filaments which reveal the airflow. And on hand to help us see the way that the airflow is affected by the design of a plane's wing was a Cambridge Don, Dr. Len Squire.
No, I'm going to put a shape like this, which is an actual wing-like section of the tunnel.
To understand what's going on, think of the smoke filaments responding in the same way as the pieces of paper we blew between at Leatherhead.
Again, the tunnel is settling, and you'll see that in this case, again with the aerofoil pointing directly into the wind, the flow on both sides is very similar. I will now increase the inclination of the flow, and now it is very obvious that here, these two filaments are a long way apart, so the air is flowing very slowly there. Here, they are very close together, and you can see that the air must be going faster. Can you see that? Yes. Now, I will try a different way of looking at it. At the moment, everything is steady, so we're just looking at speed by the distance between the filaments. What I will do now is to stop the smoke and suddenly turn it on again. can you see that the smoke over the aerofoil is going much faster? And we can increase the lift by just increasing the incidence a little more. And now we've really got a lot of lift on that aerofoil at the moment.
So if the pilot just simply puts the nose of the aeroplane up, just doing that will increase the lift from the wings?
That will happen, yes.
Because of the increase in angle? Okay.
Another thing one can do, and you've probably all seen when an aeroplane takes off or lands, that the pilot adjusts the shape of the wing so that flaps come down at the trailing edge. Now rather than changing the flap shape, I'm just going to put in a model with a flap already bent down. If you look at this aerofoil, you'll see that the front is parallel to the airstream. And so, thinking about our aerofoil before, we wouldn't expect any lift on it at all. But you see that even in this case, this streamline is very close together, whereas these are separated. So that again, there is a high pressure here and a low pressure at the top. And that is happening, although all that we have done in this case is just to turn down the trailing edge. It's affecting the whole of the flow around the wing. And this is what the pilot is doing at takeoff, because in this case, by turning the flap down, he is generating lift, and then he can get more lift by increasing the incidence of the aerofoil. So that if I now increase the incidence, you see, we're adding the effect of the flap to the effect of the angle of attack. And you're increasing the lift.
The only thing I'm not quite clear about is that if the flap gives out an additional pressure, why isn't that incorporated into the wing design in the first place?
Well, that's a good question. Length. Because, in fact, you remember when we talked about the various forces, there are the forces of lift and drag. I haven't mentioned very much about drag, but in fact, when you put the flap down, you get an awful lot of drag. So, in the normal configuration, when you're flying through the air or cruising, you want the least drag.
Oh, I see.
So you don't have the flap down.
Yes,
Whereas taking off,
yeah.
you must have the lift.
Yeah.
You have to put up with the drag.
Yeah, I've got it now, thank you.
Well, you're nearly at the end of your voyage of discovery, and I'm almost ready with your champagne question. But before I do that, I want to read back to you the passage that you all read at the beginning of the week and didn't understand. So here it is again. Listen carefully. In an airflow of constant density, moving at subsonic speed, pressure and velocity are related inversely. Thus, the air which is forced to speed up, flowing over the curved upper surface of an aeroplane wing, will give a reduced pressure. Since the air flowing below the wing is slowed, giving a higher pressure, lift is generated. Well, what do you think? Do you understand that now? Cara? More than you did at the beginning. Okay. Randy? You do. Definitely understand it. All right. James? You really do. Well, why don't you try telling me then, in your own words, what you think that passage means? Who wants to go first?
I think it's saying that when the thrust of an airplane is generous, it forces the airflow to become faster than it would be. And therefore
Faster than it would be where?
if it was standing.
Yes.
And the faster the flow of the airplane, the faster the airflow.
Well, the faster the air pressure over the wing,
Faster the speed of the air.
the speed of the air trying over the wing creates greater pressure below the wing, which creates lift.
Okay. Is that right, Randy?
The way I've understood it is that when an airplane moves through the sky, the airflow is all around the plane. But by moving the wings and the way the wings are actually designed, the air that's flying over the top of the wing is actually moving faster than the airflow below the wing. Therefore, the pressure that's on top of the wing is decreasing. And the greater pressure is under the wing, therefore that creates the lift.
As far as I can tell, that's exactly what that passage is saying. And you didn't understand that at the beginning of the week?
No.
And you do now. So now for the champagne question. Imagine that a pilot is flying a plane and he's climbing. The plane is ascending. What is one thing the pilot could do to level the plane out? Okay, so you've got an answer. What's your answer?
Just flat.
The flats. What should the pilot do to the flats?
Straight.
Okay, well, I'm awfully sorry to say that is in fact exactly the right answer. So, that having been said, I'm going to open this bottle of champagne.
I thought we got it wrong.
Are you ready? Okay. While I'm doing this, you might think about something else as a bonus. And we might even have the second bottle. There's something else that the pilot could do after adjusting his flaps just to level the plane. Is there anything else? Ah, well, what can I say? Exactly. Reduce the thrust, because thrust and lift are related in a plane, so if you have less thrust, you have less lift. What can I say? I think better give Mandy the first glass here by getting the second one right. Tara? Okay. To a better understanding of science. Cheers. Okay, well tell me. You've had a week of this. You understand something now that you didn't before. Has it changed your view of science?
Yes, it has, but the way we've done it is so good. As far as I'm concerned too, because it's textbooks. I think I shun the kind of explanation that you find in this. But because we've been able to go through things physically and being shown things visually, I find it much more approachable.
Okay, so the hands-on has helped.
Yes.
James?
I live in somewhere near the Battersea heliport. And all of a sudden I got curious about helicopters, and they haven't got wings.
Well, that's right. I mean, the fact is we've learned something, but there's an awful lot more to be understood about how planes fly than we've had a time or opportunity to do. And of course, there's a tremendous lot more to understand about the universe, but there's a way into that with the same kind of practical experience that you've had this week. I mean, what about this over here, for example? I've got a simple truck with a ball in the back. Watch what happens to the ball.